Good morning, everyone. So in the last few classes, we saw broadcast channels, and before that, multiple access channels. So we've been talking about a number of simple information theoretic models for single user and multi-user systems. And our discussion was mostly limited to discrete memoryless channels where with finite input and output alphabets. But we know that these ideas can be extended to infinite alphabets as well. And in particular, we saw that we also derived capacity regions for Gaussian single user channels as well as multiple access channels and broadcast channels. Right. So these, uh, so our discussion on Gaussian channels were typically limited to the following channel model, where the received uh, symbol at time t is equal to maybe some constant times the transmitted symbol at time t plus some additional noise which was assumed to be Gaussian. Right? And so this is in the single user case, but if it's, let's say, a multiple access channel, then you have g1 x of t, x1 of t plus maybe g2 x2 of t plus z of t. And if it's a broadcast channel, then you have a y1 and a y2, which follow similar a similar channel model. Right? But now let us look at wireless channels, and we'll see what kind of challenges they throw up when we're talking about deriving the capacity regions or deriving the best achievable rates for communication. And we'll see that these are significantly different depending on what kind of a fading model we consider. So before I actually get into channel models, we'll have a brief discussion about what exactly fading constitutes, and maybe a very high level discussion about what are the consequences of fading. So what kind of imperfections exist in wireless channels, and what kind of models these lead to, and depending on the kind of model you have, the behavior of the channel can be drastically different. So we'll see that in certain cases we can define a capacity, but in certain other cases it's not possible to even define the standard notion of capacity. Okay. So in previous classes, we've seen discrete memoryless channels, discrete memoryless multiple access channels, and discrete memoryless broadcast channels. Okay, and we'll use those ideas to derive inner and outer bounds, and also the capacity regions of certain wireless fading channels. Okay, so in some sense, this is going to be an application of various tools that we have already studied. There will also be certain tools which we have not formally proved but use very similar ideas, and I perhaps I won't give a full proof of all of these. What is important to know is how to use these various information theoretic tools, and how to apply these to more practical channel coding scenarios, more practical channels such as the ones that we see in wireless communications. All right. So, any questions regarding the topics we've discovered, we've discussed so far? Okay, so let's talk about wireless channels. Right, so these are channels which model basic cellular communication systems or Wi-Fi or even satellite communication for that matter, right? But typical examples include cellular communication, uh, things like Wi-Fi, Bluetooth, long distance communication such as satellite communication, etc. Right? And these channels are different from let's say wireline channels, where you have maybe cables going from the transmitter to the receiver, or optic fiber channels. All of these behave differently, and as a reason, there's no one system which fits all of these kinds of channels. And we'll see what is different about wireless channels than let's say wireline channels. All right, so every channel has its own set of imperfections. So let us just have a brief discussion about what are the consequences of many of these imperfections, right? So, so the most common imperfection in any channel for that matter is absorption, right? So you have absorption losses in any channel, right? So let's say that that the transmitter sends maybe 10 milliwatts of power. The receiver is not going to receive 10 milliwatts of power, right? Some of it is going to be absorbed by the environment. For example, it's going to be absorbed by space, by the air surrounding us, and there are other objects around us which absorb some of the radiation, right? So 10 watts of power transmitted doesn't, sorry, 10 milliwatts of power transmitted doesn't mean that you get 10 milliwatts of power at the receiver. The receiver could get maybe 1 milliwatt, right? So what other kinds of imperfections do you see in wireless channels other than absorption? Right? What happens? Yes.
So the scattering.
Okay, so scattering.
Reflection.
Okay, good. You have reflection. What else?
Refraction also in this.
Sure. So, well, diffraction, let's just put it under reflection. Right? So anything which sort of deviates the path of the signal. Okay, so what else? So there could be multiple users, right? So what does that result in? Multiple users, or could have multiple transmitters in general.
Multipath feeding.
We've not yet seen what multipath fading or what is fading yet. But what happens if you have multiple senders?
So interference. Okay.
Exactly, interference, right? So these could be, yeah, we could have interference due to various sources, maybe because of multiple transmitters, and there are other radiations as well, other devices, which say microwave devices, which emit certain amount of radiation. This may be negligible in certain cases, but in certain applications, certain sources of radiation might have a significant impact. So let's just club all of this under interference. What else?
Atmospheric attenuation.
Yeah, so let's call all of that, put all of that under absorption, right?
Oh.
All of those are absorption losses that leads to attenuation. So then there's noise, right? There's additive noise because of various sources, and these could be either due to, yeah, atmospheric effects, but some of the noise is also introduced by the components that you use, both at the transmitter and the receiver. So let's just put this under something like additive noise. Typically additive. Right? So generally, these components lead to multiplicative components of noise, whereas some sources of noise contribute to additive components, and then interference, of course, is typically additive. Right? So in any wireless channel, you have superposition and then attenuation. Right? So you have both addition and multiplication, and so you can always, in general, if you wanted to have a discrete time model uh, for wireless medium, then you could always say that y of t is equal to some function of x of t, where x of t is the transmitted signal, plus some, or let's say in general, this could be a function of x of t and all sources of interference. So let me call this x bar of t plus z of t. Okay, and typically we want, as much as possible, we want simple models for wireless channels. So the most common model is to say that the channel, the wireless channel, behaves like an LTI system. Right? So it's a linear time invariant system, and for most wireless channels, this is a reasonable enough approximation. Okay, but let's see what other challenges wireless channels pose as compared to other kinds of channels, and what exactly we mean by fading, right? So let's consider the simple example where you have one transmitter, and let's say you have one receiver, right? So let's think of the transmitter as a base station and the receiver to be a cell phone, right? So we have base station and whatever user equipment or the cell phone, right? So in absence of all other losses, so suppose we wanted to look at each of the impact of each of these effects. All right, so what could happen? So if there's just a direct line of sight communication, if there is nothing else around suppose that both the transmitter and the receiver were placed in free space, or let's say the atmosphere, then the only component we would see would be just an absorption loss. Right? If there were no other kinds of reflectors or anything else, then all we would see would be absorption loss. So that would mean that the received signal would be some constant, let's say g times x of t plus maybe z of t, because there could be some kind of additive noise. Okay, and this is the model that we mostly worked with in our previous discussion. So this was the Gaussian channel that we always used to consider, and this does not take into account any of the other effects. And in many cases, this is a reasonable model for wireline systems, right? You communicate through, let's say, a certain cable, say copper cable, and you mostly have the most significant effects are absorption, attenuation essentially. And so y of t equal to g times x of t plus z of t is a reasonably good model. Okay, but now what what does what does a wireless channel provide in addition to, let's say, wireline channels? So one main feature of wireless channels of wireless systems in general, this could be this is a cause. I mean, this is also a benefit, but it also causes a problem in terms of system design, and that is mobility. Right? So wireless communication systems allow there to be relative motion between the transmitter and the receiver. So even though perhaps the base station is fixed, you have the cell phone in your hand, but then you can move around freely, right? And that's a major difference. That's the main feature, or one of the main advantages of wireless systems. But then this also causes the channel, the effective channel from the transmitter to the receiver to behave in a certain way, and that makes it automatically much more challenging. So let's look at these features. All right, so let's suppose that we have one transmitter and one receiver. Okay, for now let's assume that they're stationary. But let us suppose that if you look at the base station, the base station is typically mounted on some tall tower in order to give sufficient coverage, in order to there to be a significant line of sight component. But note that so there is going to be a line of sight component from the transmitter or the base station to the receiver. But note that this is not the only component, right? Even if there is no other reflector, suppose that you're in an empty field with absolutely no other reflector around you, there is still more than one component which is received at the receiver. Can someone tell me what this is? Suppose that there's no other object around you. You're in an empty field, and let us kind of model these wireless transmissions, the wireless signals, using rays, right? So there is one direct component, one ray coming from the transmit antenna to the receive antenna, right? But there is actually one more component that you will have from the transmit antenna to the receive antenna. Can you think of what that could be? Is it possible for the signal to get reflected off something?
So from ground.
Exactly. So even though it's a completely empty field, there is one reflector, and that is the ground, right? So there is some absorption by the ground, but in general, the ground doesn't completely absorb radiation. Some amount of it is going to be reflected, right? So effectively, even in this very simplistic model, where you have no other reflectors around you, even though you're in an empty, in a completely empty space, there is still a component which is reflected off the ground, right? And depending on where you're located, even if you're stationary, this reflected component can potentially significantly degrade the the communication, the signal from the transmitter to the receiver. Because every time a signal is reflected off any kind of object, there is typically a change in the phase, right? And also the distance of this ray, or uh, the distance which is traveled by this particular signal is different from this particular signal. So in other words, this second component, let me mark this in blue. So the blue component can potentially cause destructive interference, or maybe constructive interference at the receiver, right? So the blue component interferes with the green component because so maybe there is a certain number of wavelengths traveled by the green component. So the distance between this the distance along this path is a certain number of wavelengths, whereas the distance along the blue component could be a different number of wavelengths. Right, so this is a longer path. Excuse my bad drawing, but the distance along the second component is different from the distance along the first component. So it's possible that, and what is received over here is the sum of the green component and the blue component. So this could lead to self-interference. Right, so in other words, what is received at the receiver, so y of t is equal to let's say h1 x of t minus tau 1, right? Because what you transmit at a particular instant is received at the receiver after a certain time instant, right? After a certain amount of delay, because the signal actually has to propagate through this, plus h2 x of p minus tau 2, because the distance that is traveled along this path could be different, plus z of t, right? And if and typically this tau 1 and tau 2 are not too different from one another, right? Because typically the distance traveled in the second component is approximately the same as this component. So but depending on the wavelength of or depending on the frequency or the wavelength of transmissions used, this could lead to this could potentially lead to destructive interference, and this could lead to destructive interference. All right, and in particular, if the receiver antenna is very close to the ground, right? Whereas the transmit antenna is mounted really high up, something which is very commonly seen in cellular communications, typically the downlink of a cellular communication system. It turns out that the amount of power received, the output power, or let me call it received power, in fact turns out to decay very fast. In particular, it decays as r to the minus 4 times the input power. where r is the distance between the transmitter and the receiver. Okay. So even though there is just one reflective component, and both the transmitter and the receiver are stationary, this just one reflective component can lead to a significant deterioration in terms of the amount of power that is received. Okay, I won't do all of this, so I will not prove any of these mathematically. If you're interested, you should go through either wireless communications course, but if you're interested, the following textbook is a very good introduction. So it's Vishwanath and Say. Fundamentals of wireless communication. Right, so this is a very good reference for the basics of wireless communications, and it has some very nice simple models where of course this is sort of the simplest model. You have one transmitter and one receiver, and there is a reflection of the ground, and this itself leads to a significant amount of attenuation. Right, and this is in the case where the transmitter and the receiver are sort of stationary. Right, so as soon as there is mobility, right, so when you have the transmitter and the receiver moving with respect to each other, so let's assume that the transmitter is stationary but the receiver is moving, right? So the receiver is in motion. Then of course there is a direct component from the transmitter and the receiver. There is a direct component of the signal from the transmitter to the receiver, but then there are also many reflected components. There are reflected components from the ground, and if there are other objects around you, then there are reflected components of that object. Right, so the signal that is transmitted gets reflected off different objects, the ground, other buildings, or let's say hills, trees, and everything else. Some of the components or some of the energy is absorbed by those objects, but a large part of it is reflected. And what the receiver gets is a sum of the signals received along all of these components. And if the wavelength of the signal is comparable to the distance, to the difference in uh, the distances along each of these paths, then you once again have self interference occurring. So you can have destructive interference occurring at the receiver, right? But when the object is in motion, there is something else that is happening. Firstly, there is no. So when you are in motion, there are two things happening. Firstly, the distances along these paths these change with time. right? So note that let's assume that there is even no other reflector, even if there is just one reflector. If the receiver is in motion, then let's assume that this is going away from the transmitter. Then the length of this path and the length along this path, this changes with time, right? And in particular, if when you're moving, the signals could, depending on the distance along these paths, these two signals could either add constructively or they could add destructively, right? So if you have the following situation, that at the receiver, so this is along the direct component, whereas if this is what is received along the uh, reflected component, then these signals add up, leading to constructive interference. But then it's also possible that depending on the distance traveled along this path, these could also add up destructively, right? In which case, it is the difference, what is received is the sum of these two components, which is close to zero, right? So this could be close to zero. All right, and since the receiver is in motion, you keep moving from regions of constructive interference to regions of destructive interference. So, so depending on how fast you are moving or how slow you are moving, you could rapidly go from regions of constructive interference to destructive interference, and vice versa, right? And as a result, so you move between regions of constructive and destructive interference. So as a result, the attenuation factor this varies with time. Right? So and you would have noticed that in practice as well, right? So at certain points, if you have your cell phone with you, you keep your cell phone in a particular place, and then you notice the number of you can see how much reception you have, right? So in your cell phone, at the top right corner, you have these bars indicating how good your reception is. And maybe at some point, if you keep your phone, you'll have maybe 2 bars of reception. But then just by moving it a little bit, those 2 bars could just jump to 3 bars or 4 bars, right? And when you're speaking on the phone, if you're walking as you keep speaking, you will notice that sometimes all of a sudden the signal drops. You're not able to listen to the other person anymore, and by moving a little bit, you see that the signal reception significantly improves. Right. So if you keep moving, this attenuation factor will vary with time, and and unless you're perfectly stationary, this attenuation factor won't remain constant. All right, and how fast the attenuation factor varies with time really depends on what is the speed of or what the relative motion between the transmitter and the receiver is like. Right, so this is characterized. So how fast the attenuation factor varies with time is characterized by what we call the coherence time. Right? So this determines how fast the attenuation or how fast the amplitude, let me call it attenuation, varies with time. So mathematically speaking, you have the received signal being equal to some channel coefficient times the transmitted signal. So the channel coefficient varies with time, and how fast the channel coefficient varies with time is determined by what is the coherence time. So this is a very loose definition of the coherence time, but maybe a slightly more precise definition is perhaps a better definition uh, is how long the attenuation factor or coefficient remains roughly the same. So there are different definitions of what exactly the coherence time is, but for our purposes, we'll say that this is the duration for which the channel coefficients remains constant. Okay, after the coherence time, the channel coefficient changes. So within a period of equal to the coherence time, the channel coefficient remains constant. Okay, so this is one effect of relative motion, but there's another effect of relative motion between the transmitter and the receiver, and that is a Doppler shift. Right? So the Doppler shift is more noticeable uh, if the transmitter and the receiver are moving very fast. So if you're moving very slowly, then this doesn't really happen. What is a Doppler shift? A Doppler shift is a change in the received, change in the frequency of the received signal. So you could be transmitting. So you transmit a signal at perhaps frequency f0, but depending on whether whether you are moving away from the transmitter, whether the receiver is moving away from the transmitter or closer to the transmitter, what is received could be at a frequency f0 minus delta, or it could be at a frequency of f0 plus delta, because there is a Doppler shift. Okay, and how much this how much the frequency varies is characterized by what is called the Doppler spread. So you say that the Doppler spread is delta if the received frequency is between f0 minus delta and f0 plus delta. Okay, so this is, so these are two consequences of motion, right? One is that the attenuation varies with time, or the channel coefficient varies with time, and how long the channel coefficient remains constant is what is called the coherence time. And due to relative motion, there is a Doppler shift, and since you have multiple components which are received, so there could be reflections. So as a result of these reflections, what is received is not a single frequency, but it could be a range of frequencies. Right? So for example, if there is one single transmitter and you have a receiver who is moving away from the transmitter. Now, there is one component, right? So so this is one component from the transmitter directly to the receiver, and in this case, you are moving away from this source, right? But on the other hand, if there is a reflector somewhere else, then there's one more component which is reflected off this particular object and received by the receiver, and this is in some sense behaves like another source. All right, so it is a reflection, but in this case you are moving away from the source, whereas in this case you are moving towards the source, and that is why what is received, the signal that is received, is not a single frequency anymore. This could be a range of frequencies. There's one component f0 minus delta, and there could be another component which is f0 plus delta. All right, and so it's so there is a spread in terms of the frequencies that are received by the receiver, and how much this frequency can vary is characterized by the Doppler spread. So the faster you move, the higher the Doppler spread is going to be. The slower you move, the lower the Doppler spread is going to be. Okay, and this holds even if the reflectors are in motion. So it's possible that the transmitter and the receiver are stationary with respect to each other, but if you have many reflectors which are moving fast enough, then once again you will have a Doppler spread. Okay, so this is one component of a fading channel, which is the coherence time. Second component is the Doppler spread. There is a third component, and that is so note that the distance traveled by the signal along this path is different from the distance traveled along this path. So x of t, some particular symbol transmitted at time t, it takes a certain amount of time to reach the receiver, but along this path it takes a longer time to reach the receiver, right? So in some sense there is a difference in the time taken by a particular signal to be received along the shortest path and the longest path. So maybe the delay along this path is tau1, whereas the delay along this path is tau2. And if you're sampling at a much faster rate as compared to, let's say, tau1 minus tau2, then the symbol that is transmitted at the current instant is received maybe at the current instant, but a component of that could be received in the next instant as well, right? And that is characterized by what is called the delay spread. Right? And the delay spread is essentially the difference between the times taken it's a amount of time taken for the signal to propagate along the longest and the shortest paths. Right? So in this particular example, it is the difference between the time taken by the signal to propagate along the green path minus the time taken to propagate along the black path. Okay, so if the delay spread is significantly large, then there's a spillover of the energy transmitted at the current instant, which spills over to the next time instant or maybe time instants after that. Right? So each of these, so depending on how large or how small each of these parameters are, the nature of the channel is different, right? And that leads us to our categorization of various fading channels. All right. So you have various kinds of fading channels, and there are again there are different ways of characterizing these, but we will characterize these based on just two of the parameters which are generally the most significant. One is the delay spread, the other is the coherence time. So note that the delay spread is how long it takes uh, for the signal to propagate along the longest path versus the shortest path, right? So depending on the delay spread, right? So if the delay spread is small, the delay spread is much smaller when compared to the wavelength, and depending and compared to the sampling rate, we call the channel to be a flat fading channel. Whereas if the delay spread is large, then we call it a frequency selective fading channel. Right? So let's see what kind of models these lead to. So if the delay spread is very small, then essentially whatever you transmit will be received after a certain delay, right? So let's assume that we have a discrete time model obtained after all sampling and ADC and everything at the receiver. So one model y of t is equal to, let's say, x of, let me use y of, yeah, let's say y of I is equal to x of I plus z of I. So maybe h of I, x of I plus z of I. Okay, so this would be a flat fading channel, sometimes called a frequency flat channel. Now, on the other hand, if the delay spread is large, then y of I is h0 x of I. But there are also components from which were transmitted at the previous time instant and the time instant before that, and so on. All right, so hi, so let's say h1 x of I minus 1 plus h2 x of I minus 2 and so on plus z of I. Right, so this is a typical frequency selective model. Right, so if the delay spread is large, then you have spillover from the previous time instance. Whereas if the delay spread is small, the channel is flat fading, and you don't have any sort of spillover, whatever is received at one instant is received in whatever is transmitted at a particular instant. Almost all of that is received in the same time instant, or maybe after a constant delay. Right, so this is a categorization of channels based on the delay spread. Now, depending on the coherence time, once again you can categorize channels into two. If the coherence time could be small, it could be large. So I'm deliberately not quantifying exactly how small the coherence time has to be or how large the coherence time has to be. Sometimes this is not exact. There are different ways of categorizing based on the coherence time, but loosely speaking, if the coherence time is small or the coherence time is large, we'll have different kinds of channels. Right? So if the coherence time is small, then it means that the channel is varying rapidly. right? The attenuation factor is varying rapidly, whereas if the coherence time is large, then the channel remains roughly the same. All right, so if the coherence time is large, we say that the channel is slow fading. Whereas if the coherence time is small, the channel is rapidly varying, so we call it a fast fading channel. All right, so a good model for a fast fading channel is, at least for a certain for one coherence interval, so sometimes called the coherence. So the coherence interval is a period where the channel coefficient h is constant. Right? So within a coherence interval, we have y of I to be equal to, again, if the channel is, let's say, frequency flat, then y of I equal to h times x of I plus z of I, where where within a coherence interval h is going to remain constant. So this is for a slow fading channel, whereas for a fast fading channel, the coherence interval is going to be very, very small. So this is true for any, in any case. So this is true for within coherence interval. Let us say the kth coherence interval. This is hk x of I plus z of I, where this depends only on which coherence interval you are in, and within a coherence interval you could be transmitting multiple symbols. So we'll say that the channel is fast fading if the coherence interval is much smaller than the block length n. Whereas if the coherence interval is comparable to the block length n, maybe it's order n, then we'll say that it is a slow fading channel. All right. So it's a slow fading channel if it is if the coherence or the coherence time is really large, whereas if the coherence time is much smaller than n, then we'll call it a fast fading channel. Right. So there are, depending on the coherence time, you categorize a fading channel into slow fading or fast fading. So a slow fading channel is one where the channel coefficients do not vary much with time, and a fast fading channel is one where the channel is rapidly varying with time. And depending on the delay spread, you categorize the channel into flat fading versus frequency selective fading. So in a frequency selective fading channel, you have the received symbol depends on the previously transmitted symbols as well. Whereas in a flat fading channel, it depends only on the current transmitted symbol. The received symbol transmitted at a particular instant depends only on the symbol which has been transmitted at that particular instant. All right. And note that if the channel is frequency selective, then it has memory. So it is not memoryless. right? Whereas for a flat fading channel, a flat fading channel can be memoryless, right? So all of this again depends on the coherence interval as well. So this depends on whether it's a slow fading channel or a fast fading channel. And that is why we will assume that the coherence interval is either very, very small or the coherence interval is very, very large. So we'll make two assumptions, either so fast fading, we generally assume that the channel coefficient is IID across time. So it really varies in every single time instant or every single channel use. And in slow fading, we will assume that the channel coefficient is constant. Right? It's a random variable, but it remains constant for the entire block length. Okay, but there are also things, regimes in between. So wherein the coherence interval can depend on n. It could be maybe log n, or it could be say square root of n, and so on. And each of these lead to uh, different issues. All right. So we'll stop at this point. Are there any questions? So this was a very quick introduction to, or a quick recap if you've already taken the wireless communications course. So a very quick recap of wireless fading channels. We don't have the time to go through it in detail, but you should definitely go through the textbook by Vishwanath and Say, or a related textbook to really understand things better. Okay, so in this course, we'll mostly talk about frequency flat channels, and they could be either fast fading or slow fading. Okay, so if there are no questions, then we'll continue this discussion in the class tomorrow, where we'll start with single user fading channels, and then once we get some understanding of that, we'll get into multi-user fading channels. Right, so see you then.